Hey, what is up, everybody? Welcome to. I'm gonna go back to chapter 1 now. We have chapter 9, and our chapter 9 is going to be law of sines and law of cosines and all that stuff. We're done with that. We're done with trigonometry. Now we're gonna go back to the geometry part of this lesson. And I'm sorry if there's going to be some background noise because there is I don't have my own room. Obviously, I share a room. So, anyways, we are going to start and looking at cross sections in solid to revolution. I'm only going to teach one lesson out of this unit, kind of, because this unit is you're already supposed to know everything there is to like perimeter modeling and area modeling. If you go to pre-calculus in the next year, you'll be doing a lot of that, and the stuff in here in this book isn't nearly as advanced as the stuff that you're supposed to know from pre-calculus and calculus. So that's why I'm not actually going to go through 1.1 and 1.2. So here's a question from the homework. I'm going to put a question from the homework at the beginning because this question is basically the whole lesson. it's serious. I'm serious. Cross section's a shape. You slice the three-dimensional shape, and the shape that you slice the three-dimensional shape, and this two-dimensional shape that you get from that slice of plane is your shape, right? So if you want to get an isosceles triangle from the shape, well, we're gonna draw a plane right here, right now from this. You'll probably get a plane something like this, right? And then that'll give you, I don't know, like this. And that's a triangular cross section. See, that's equal to that, right? And if you want an equilateral triangle, you can just cut it like this. There's nothing to teach here. It's just intuition. The more intuition you have, the the easier it is to visualize the cross sections, right? So if you cut it like this, you have an equilateral triangle. This equal to this equal to this. Scalene triangle. Well, if you wanted a scalene triangle, you could just go any random kind of like this. You can go like this kind of. That'll get you a scalene triangle. That'll get you like this, and then like this, and then like this. So this would be your shape. It looks like an isosceles. Probably is. But with a scale, if you want a scalene triangle, you can just cut like at a weirder at a more x angle, at a more oriented angle, like more a flatter angle, like something like this, right? Rather than something like this. So if you want a parallelogram, the easiest way to get a parallelogram is just to cut from here. You can just cut like this, right? If you cut like this is just to build your intuition about the shapes. If you cut like this, you'll have this parallelogram right here, right? Because this is s square root of 2, that's square root of 2, and that's the side. And if you want a pentagon, which I don't know how, I honestly don't know how you are supposed to get a pentagon, but you can kind of cut like this if you want a pentagon, right? And this will give you, actually, that'll give you something more like another parallelogram. But if you cut like this and then you go down a little bit, you will get, now actually, if you cut like this and you go down a little bit like this, so you can cut that edge off, you could see that this will kind of give you two sides right here. This will give you two sides right here. So the shape that you will be getting is kind of like this, and then you will get a shape like that, right? That's not a pentagon, to say the least. That's a hexagon. Actually, is that a pentagon? 1, 2, 3. 1, 2, 1, 1, 2, 3, 4, yeah, that is a pentagon, right? 1, 2, 3, 4, 5. That's a pentagon. If you want a hexagon, you just bend the, you can just bend the thing kind of like this, and then you want to cut this over this, and it's weird. It's a weird shape to visualize. But basically, these are the shapes that you can get from cutting a cube, and it's really interesting. Um, but that's for you to figure out. So we're gonna go to the next. What shapes can you get from you when you slice these? You can get a lot of shapes. Let's be honest, you can get a lot of shapes. But the shapes that you can get that you can slice these are, I'll let you think about it for a second, and then I'll come back and then go for 5 seconds, and then I'll come back in 5 seconds. Okay, so the shape that you can get from this, if you cut it straight through like this, the shape that you will get is, well, this extends over here, this extends like this extends over here, so you can have a line like this, which gives you a trapezoid. If you cut the shape like this, like straight through the center, kind of like this, this looks really messy. You will get a shape like this, right? A shape like this. So I'm actually gonna draw it in red. So you'll get a shape like this, which is a triangle, right? Equilateral triangle. Um, so I'm gonna draw the shapes that the cross sections that I figured out. You can also cross the shape like this, which will give you a isosceles triangle. Let's say if you slice the plane like this, right? If you slice the plane like this, you will get yourself an equilateral. You will get yourself one of these, which is an isosceles triangle. Let me use a different color, green. Isosceles triangle. So those are some of the shapes that you can get. Of course, I'm not going to tell you all of the shapes because I don't know all of the shapes myself. So that's why I'm not going to tell you all of the shapes. Next is the cylinder. The cylinder is pretty simple. I'm going to give you 3 more seconds. Okay, so with the cylinder, there are 3 shapes that you can get. To my knowledge, there are only 3 shapes that you can get. There might be more. There might be a shape that you can get for slicing like this, like this, but I'm not sure, right? So the 3 shapes that you can get is a circle. If you slice it flat, like completely flat, you'll get a circle. If you slice it kind of at an angle like this, you will get an ellipse. You will not get a circle. You will get an ellipse. So it'll be kind of like this. It'll look something like this. It won't be a circle, right? I'm bad at drawing, so there you go. Or you can draw. You can you can have the plane cut like this, which will give you a rectangle. This will give you a rectangle, right? So circle, ellipse, or rectangle. Now we have another one. This is 2 cones, and you normally see this in something called conic sections, um, which I will hopefully introduce later. Not in this course. Not in this course. I will hopefully introduce, I don't know, in some pre-calculus review, when I have to review for the concepts for pre-calculus, prepare you for calculus. However, there are certain conic sections you can get as well. For example, this conic section right here, you can guess. This conic section right here, like this, I hope you can guess what that is as well. So you can get those two conic sections. You can also get this conic section right here. Right? You can get this conic section right here. And you can finally get this conic section right here by slicing through the whole thing. And the conic sections are, they're called conic sections because they are sections of a cone. The conic sections are the circle, just a regular circle, right? The ellipse, just not the most regular ellipse ever, but it's an ellipse nonetheless. A parabola, you can get a parabola. So that's pretty interesting, right? You can get a parabola. Okay, that's a really ugly parabola. Parabola like this, right? Actually, let me. There you go. That's a parabola. This whole thing, this whole episode is just gonna be me drawing. And then the hyperbola. So it's gonna look something like it's gonna look something like this. There you go. It's gonna look something like this. So like this, like this, like this, and like this. Right. So those are the those are the four conic sections of the slices. So we're gonna do some problem solving. We have a mason that uses a concrete saw to cut the blocks like this against the diagonal. So identify the solids that are being cut, formed by the cut. So this will get you, well, if you slice a something like this. Actually, I'm gonna draw it out. I'm gonna draw it out. I'm not too bad at drawing. At drawing solids. So you slice something like this, and then you slice it across this. I'm gonna draw a big plane. Right, and then you take, and then you get this cross section. Your two remaining shapes are going to be this and this. It's like two cheesecakes, right? It's going to be two cheesecakes. It's not cheesecakes. They are actually pretty obvious triangular prisms. They're triangular prisms. They're not like a nice triangular prism. They're kind of a naughty triangular prism. Find the perimeter in the area of the cross section. Well, first of all, we have this as 100. This is 440. So this is the Pythagoras theorem because, well, it's a uh what is it, right angle. So we have 100 squared plus 440 squared equal c squared. So 100,000. I don't want to work this out. 440 squared is 4 times 80, 19 3600. So 2,3600. I'm pretty sure you already know how to do the Pythagorean theorem. I don't need to do the Pythagorean theorem again. So this is 203,600. Add that to the 215. So the answer will be for B. The perimeter is 2 times 215, right? Because that's the square root. Wait, no. That's the square root, and that's 215. So 2 times 215 plus square root of 203,600. And then the area is going to be, notice that it's not a square per se. It's not a square. And because is it a rectangle? Is it a rectangle? Well, if you take this line right here and then you drop it down, that's a diagonal, that's perpendicular, and these are perpendicular as well, so they are a rectangle. That's the great thing about this thing, is it's a rectangle. So we can actually just multiply the two together, which will get you 203,600 times 215. Let's simplify this square root. The square root simplify is that's gonna get you 509. So 509, so 220 times the square root of 509. And I'm pretty sure this can be simplified as well, like 167 or 169. No, not 169. So I don't think this this might not be able to be simplified. So multiply this by 215, and that's your answer, right? It's about it's a lot. Okay. The block has a density of about two. Nah, I'm not gonna be doing this because it's just a density question. It's just there to distract you from what we're supposed to be learning, because this is not what we're supposed to be learning. Next, solids of revolution. This is a really interesting concept. It's gonna be, you're gonna see it a lot in calculus. And solids of revolution means there's a line, there's a shape, a 2D shape. So basically, we're basically doing the opposite of the cross section thing, except there's no plane cutting through it. It's more like just you have a shape, and then you have infinite amount of it, like 3D printing it over a line, right? You 3D print it over the whole line. I'm gonna draw through this shape like this, right? So you go from here, then you go right, and then you go at the bottom too, and then every bit in the middle of it also gets rotated, and then you'll end up with a cylinder. So we're gonna try to visualize some of these. If you rotate it over like this, we're gonna draw some of them. We're gonna draw kind of contour plots. So we're gonna draw circles. Right, we're gonna draw circles like this, and we're gonna draw lines like this of smaller and smaller circles like this, to illustrate that, to illustrate our shape, right? So we're gonna draw lines and then circles, and then lines and then circles. Okay, you know what? I'm gonna just draw a big circle right here. All right, and then we can obviously connect the right there. We can connect the outsides together, and this what we'll get. It looks like an hourglass, right? So similar to this, we can draw a line right here, and then we can draw a circle, a line, and then a circle, a line, and then a circle. If you, this is only if you can't visualize it, by the way. If you can visualize it, I would just do like that, right? If this is if you can visualize it, I'll just do that, because you already know that it's like this, and you only need to show that, and then that's it. That's the shape. It's like a double cone, right? So if you can't visualize it, do it like this, right? Because if you can visualize it, that's kind of a waste of time to do it like that. I would just do that, and then I would just do that, and then I would just do that, and then I would just connect it, right? Because that looks like a vase. That looks like what it's supposed to be, and the other one doesn't. So if you can't visualize it, you can do it like this and maybe cross off your erase marks later. But if you can't visualize it, right there, it's right there for you. The hard thing about this is you have to be able to find the surface area and the volume of the resolution as well. It's not really even that hard. But basically, if you take the volume, and if you're able to visualize it, it'll be really easy for you. So this is just obviously just a cylinder, because I already told you it's a cylinder. So there you go. You can just rotate it around the thing, and then you can calculate. So what's the surface area of a cylinder? It's the basis plus the height, right? Plus the circumference times the height. So it's circumference times the height, plus the area of the basis, so pi r squared, and then two of them. So it'll be 2 pi r times the height plus 2 pi r squared, 2 pi 1 times the height plus 2 pi 1 squared, which will get you 16 pi plus that's 18 pi units squared. And then if you want to calculate the volume, it's pi r squared, the whole circle, and then you project it infinite times down on you project it down onto the other circle, which is pi r squared times the height, which will give you 8 pi units cubed. And the surface area in this case is actually bigger than the volume. Pretty interesting fact. So anyways, we have now a something that you could visualize. You could try to visualize this. It's pretty obvious, in my opinion. It's basically just a cone, right? You could I'm gonna draw it right now. We're gonna draw it up there. It's a cone. It's not hard to visualize, but right there, right? You now know it's a cone. So we're gonna find the surface area and the volume of this as well. And whenever you have a radius right here, and then you go over the solid of revolution, notice how notice how it's the radius and not the diameter that's going through. Because now the diameter is 10. Now the whole shape's 10. Now the radius looks like it's half the base instead of the whole base. So that thing right there is the radius, not the diameter. That's what you should. I want you to know that that's the case, because if you use this and then you suddenly see that it became bigger, like 10, and then you use that as the diameter, that's not gonna work. So the cone surface area is pi r squared plus pi r times the slant height. So we have pi r squared, which is just 25 pi, and then plus pi r times the slant height. So pi r is 5 pi times the slant height, 13. This is the slant height. It's not the actual height that's right on the triangle. No, not triangle. It's not the actual height that's right on the cone. It's the slant height, right? The height that it takes for you to go from the bottom to the top. That'll give you 90 pi units squared. What about the volume? The volume is for any of these shapes, pyramid-looking shapes. This is like a circular-based pyramid. For any of the pyramid-looking shapes, it's 1/3 of the cylinder of it. So it would be 1/3 of pi r squared h, which is what I had over there. Right, so the prism, this is a circular prism cylinder, and this is a circular pyramid, which is a cone. So that's 1/3 pi r squared h. So what is our height? Well, we can use I specifically put a right angle right here to show that you could use the Pythagoras' theorem to figure out that this is 12. So 13 squared equals 5 squared plus 12 squared. And then you will be able to do it really easily by 1/3 pi 12, no, 1/3 pi 12 times 5 squared, or 1/3 pi 5 squared times 12, and then 1/3 times 12 is 3, 5 squared is 100 pi units to the third power, units cubed. And that's it. Now next we have, oh, this video is pretty long already. Oh god, I'm not supposed to show this. Oh no. Okay, that's a cone though. Anyways, so we have these, and we want to describe the solid. We want to flip the solid over on the axis that it says, and we want to draw basically a graph of it to see what it would look like. So we're gonna do that right now, right? So y equals x plus 3 is going to be this shape right here. I already taught you everything about that you need to know about functions, so there's no excuse to not know what y equals x plus 3 is, because you are probably already in the 11th grade, and you start learning these in the 6th, or younger for some of you, or older for some of you. But right here is the x plus 3, and we bound it for x equals 0, and we bound it for y equals 0. So x equals 0 and bounded for y equals 0. So the three bounds, the region of the 3 bounds is this. And you could calculate this. This is 3. You could calculate the x-intercept if you wanted to. So x is 0, so it will be -3. So this is 3 as well. And you could draw the shape if you want to. I'm just going to draw the shape right now. Right, this is what the shape looks like. Obvious. And since it's like this, we only need to find the volume. We don't need to find the slant height. it's going to be really, really easy because we could just do 1/3 pi r squared h. And 1/3 pi r squared h is 1/3 times pi times 3 squared times 3, which is 9 pi. And that's 23. 24, we have a little bit of a more complex shape right here. Well, actually, wait, I'm really stupid. It's supposed to be reflected over the x-axis, not the y-axis. So the shape actually won't look like this. The shape will not look like this. The shape will actually look like this. I am really sorry for being stupid. Shape will look like this. That's what the shape will look like. However, if you do the calculations again, the volume's still the same. So at least that's that, right? The volume's still the same. It's a cone, but the volume's still the same. Next we have ourselves -4, x equal -4. So that line will be say right there. X equal -4, y equals 0. So that's just that. Y equal 1/2 x. Y equals 1/2 x will look something like this. No, what? No. What? I'm looking at this. Y equals x will look something like this, and that's it. I think. Right. So x equal -4, y equals 0, y equal x, and we want to reflect it over the x-axis, right? So then what you'll get is this, right? It's just a solid of revolution on the horizontal plane. It's a little bit hard. It might be hard to visualize a little bit. I hope it isn't. There you go. So this, since this y equals x and it hits y equals x equals -4 right here, this point is x equals -4, y equals x, so it's y equals -4 as well. So it's -4 -4, which means this is 4 and this is also 4, right? So therefore we have the volume is equal to 1/3 pi r squared h, right? And then that's equal to 1/3 pi times 4 squared times 4. Honestly, I wish these questions were a little bit more interesting than just literally just flip over the x-axis or the y-axis, but we're not gonna have that because it's gonna be really messy. So that's equal to 1/3 pi times 64. Yeah, we're gonna need to get into calculus if we want to know any of that. So 64 over 3 pi. That's it. That's it for today's episode. That's it for the whole geometry of the whole integrated math 3. It sounds crazy, but that's all you need to know for geometry for some of you the rest of your life. And so that's all the algebra you need to know for the rest of your life. Next lesson I will do some statistics for you guys, which will be hopefully fun. I don't really enjoy statistics myself, but the questions do actually seem pretty interesting, and the high-level statistics measure actually allows you to do a lot of stuff with surveys and stuff that you're going to be getting. I know psychology, sociology, psychology, sociology, and a lot of those like majors are trying to have those have people having statistics as a prerequisite, like statistics major, or we just have there's a lot of experiments going on not this year, in the future, that are going to have to deal with a lot of statistics for just computer science and engineering in general. So that's going to be it, and I'll see you next time for z-scores and standard deviation.